I would like to give you, I would like to say a couple of words about who I am, what I do. So here you have, by the way, my contact details, uh, email address, telephone number. You can also connect with me on LinkedIn using this QR code. As said, I'm Alvaro. I am a product sales manager with focus on optics and photonics, working for Ansys Germany. I joined Ansys in 2021. I am located in Munich, Germany. And yeah, in my role, what I do is supporting Ansys partners like Kiffinsoft with any sales related questions for optics and photonics products. And for this presentation, we are gonna have as well my colleague Florin Herren. Maybe Florin, if you want to introduce yourself quickly.
Yeah, sure. Thanks, Alvaro. Hey, good morning, everyone. Nice to be here. My name is Florin Heron. I'm an optical and optomechanical engineer at Ansys. Joined Ansys now, nearly 5 years ago. I'm based in the UK, and yeah, I'll be taking over a bit of the multiphysics side of this presentation. I got a background in optical engineering and mechanical engineering.
Perfect. So with that, we can jump into the agenda of today. So first, I would like to give an overview about some key applications for optics and photonics in the space industry. And with that, I want to also give an overview about what are the challenges that companies like you need to have to face when you are working in this type of optics and photonics projects. And also, once we have seen the challenges, we will talk about the solutions that we can offer you at Ansys to face these challenges. So I will give you an overview about the different solutions we had at Ansys for optics and photonics. Then there will be a part presented by Florin, which is going to be about multiphysics workflow for a low Earth orbit satellite, with giving you an example. We will then go through learning and development materials, so where you can learn, where you can find some more materials to learn more about these products. And finally, we will finish with a Q&A session. Okay, so let's start with the key applications and challenges for space technologies. In this slide, I want to give you an overview about some examples. These are just examples about where you can apply optics and photonics simulations. There are many more, but I will name a couple of them. So the first one is surveillance and exploration. So there are many tools with optical systems and infrared sensors in this area that you can design and optimize using CMAX, Speos, and Lumerical, the tools that we have at Ansys Optics. Another key application is for guidance and targeting systems. So these systems has things like laser rangefinders and designators for detecting and tracking objects in the space, and these can be designed using our tools. Also for remote sensing tools. Remote sensing tools have optical systems and LiDARs that are set in the satellites for Earth observation, environmental observation, and so on, that can be as well designed with the optics or tools. Very important for communication system between satellites and ground systems. These needs optics design as well. Navigation and positioning for things like star trackers and gyroscopes that are set on the spacecraft and are used to provide precise navigation data for that as well. Astronomy and space exploration, for example, to design and optimize the optics on the telescopes. And last but not least, missile defense systems for the design of optical sensors on the missile defense systems that are used for tracking and identification of ballistics rockets. Again, a couple of examples where you can use or need optic simulation. So now, if we, for example, want to build an optical system that is going to be placed on a satellite, we have to think that the majority of Earth observation satellites are placed in the low Earth orbit. And typically this is between 160 and 2000 kilometers above the Earth surface. And we need to be able to design optical components that can operate in this region of the space. And here is where CubeSats can be interesting. They can be interesting because they can operate in this low Earth orbit, and they are less expensive than individual satellites. However, here the challenge is that the optical systems that you will design for these CubeSats, they need to fit into the standardized volume of these CubeSats, and you need to be able to maximize the results that you can get with this optical system. Later, my colleague Florin will explain you how you can optimize the results of your optical systems with a multiphysics workflow. But we will go into that a bit later. So let's have a look on the challenges that you might have when you need to design an optical system that will operate in the space. So we need to think of three main challenges. First, you need to reduce the time to market because you need to be faster than the competition, let's say. You need to reach a high level of performance, and you need to deliver products that can offer a high reliability. So this is very important. And for meeting these expectations, you need to be able to predict the performance of your optical systems before prototyping, because as you know, prototyping, manufacturing requires a lot of time and costs. It requires a concrete location to test the product, traveling, coordinate the data. It's a lot of work. And also laboratory testing requires also time and costs. So what is the solution? The solution is really to use simulation tools for virtual testing that will help you to save time, reach the level of expected performance, and reduce the costs. So now, what are the solutions that we can offer you at Ansys to face these challenges? So at Ansys, as you know, we are leaders in simulation software from many different domains. So from structural mechanics, fluids, electronics, semiconductors, and of course, we also focus on optics, which is here in this area. And here, if you think of this concrete spectrum, so being part of Ansys products portfolio is a great value because it offers you the possibility to interoperate with multiple tools from many different domains if it's needed. So you can interoperate with all of these other solutions in case you might need it. Okay, so if we look at the wavelength spectrum, we can see that there are multiple areas you can simulate optics. And at Ansys Optics, we are offering solutions to simulate physics that are here in this concrete area. So from infrared light, the visible light, and also ultraviolet light. So if you have any products that are where you need to visualize or design physics of light in this concrete area, we can definitely help you. So Ansys Optics offers an end-to-end portfolio that includes 3 solutions to cover all customer needs from the nanoscale up to moving to the macro scale up to the system level. And I will explain you what are the 3 solutions that can help you in these 3 concrete areas. So let's start with the nano part. So this is the first tool called Ansys Lumerical. Ansys Lumerical is the tool that we are going to use for photonic simulations of sensors, waveguides, microlenses, and other components at a chip level where full electromagnetic wave optics are required. So we can use it to design and optimize components at the nano level, like the ones that you can see here, waveguide development, sensor and emitter development, nanostructure design, high reflective and anti-reflective coating layer, etc. So all of these nano components, photonics that you need to design in your optical system will be designed using Ansys numerical. And once you have that, once you are able to conduct the light, for example, into a circuit, you need to have a macro optics component that is going to help you to get this light. And this is where you jump into the next tool, which is Ansys CMAX. So Ansys CMAX is the tool that we are going to use for modeling of macroscopic optical components with lens stack optimization and optical and mechanical tolerancing. So with CMAX, you can also analyze how thermal loads will affect your optical system. So you can add some multiphysics, and this is going to be one of the parts that we'll explain later by Florin Herren. So again, you have been able to design the photonic components or the nano components of your optical system. You have designed your macro components, things like lenses, mirrors, all of that that you need to add into your optical system. Now you need a tool that is going to help you to validate if the results that you are getting with the components that you are designed are good enough. And this is where the next tool is helping. This is Ansys Speos. Ansys Speos is the tool that you are going to use for system level modeling in full 3D environments. And I say full 3D because it helps you to simulate in a 3D environment how your optical tool will look like. And also the results that you are going to get in a 3D scene to understand if the results are good enough and are fitting your expectations. And it includes human or machine perceptions. This is to simulate how the human eye will look through your optical system, how the human eye will perceive the results that you're gonna get with this optical system, which is very, very important. It's also a tool that is used for lighting design and evaluation, and it can be used in combination with CMAX for doing a very accurate stride light analysis. And I will explain in another slide later how you can do this very accurate stride light analysis. But what I want to point here is, what I want to summarize here is that we have 3 products that can cover you with optics and photonic simulations for any use case, from the nanoscale, macro scale, up to the system scale. And the great thing about it is that you can interoperate with these 3 tools, allowing you better and faster workflows, and also a much better collaborations with different teams that might use different solutions. So moving forward, what I want to do is to give you an example about how you can interoperate with these 3 Ansys tools. And I want to show you the workflow that you will have to follow if you will have to design a camera, for example. So in this workflow, what you can see here in the white box is the steps that you will need to follow for the optical development of the camera system. This is what we call the macro design, macro optics design. Imager development, which is in red, these are the steps that you can follow for the nanoscale optics design. And finally, you have in blue here the system analysis. This is to understand what kind of results am I going to get with my optical system. So let's start with the optical development, which is the macro optics design. So you can do, for example, things like lens stack optimization and tolerancing. So to design your lenses, to put all of these lenses together, then you can do some optomechanical packaging to add some mechanics into your optics, and also do some ray tracing to understand how the rays are going through your optical system. Finally, well, then later you can do some stride light analysis. This is to understand if you are going to get some unexpected results, unexpected aberrations in your system. So you need to adapt your optical system to avoid to have these aberrations in your system. And you can do as well some structural and thermal analysis to understand if this is going to affect negatively into your optical system. On the imager development, on the sensor, for example, if you want to optimize or design your sensor, you can do things like micro lens array optimization, color filter optimization to be able to get the best results out of your sensor. And then once you have done the macro optics and nano optics components, you need to do a system analysis. And this is how you can generate a 3D scene to understand what kind of results am I going to get with my camera that I have designed with the optical components that I did so far. So here you can apply things like different atmospheric conditions to evaluate how, for example, this camera is going to work under rain, under foggy, under different sun angles. This is just to test and validate if your system is going to work as expected. And here, if you can see about the tools that we have used for doing this, is this part has been done with CMAX. So the macro optical design has been done with CMAX. The nano photonics part has been done with Lumerical. And this system validation has been done with Speos. So it is critical to be able to interoperate with these three tools if you want to have the best results out of your optics design. Okay.
Alvaro, can I
Yes.
ask a question? The thermal analysis in the center of your picture, do you only do soaks, or can you do gradients or different temperatures for different lenses?
Do you mean this one? Sorry?
The thermal analysis, yes.
Thermal analysis, yes.
Can you handle gradients in temperature? And if different lenses in the set is at different temperatures, can you do that, or is it only for soaks?
This is maybe a question for my colleague Florin Heron, who is the specialist on the thermal loads and VA data.
Yeah, we
Florin,
have.
do you know that?
Yeah, of course. Yeah, we have several ways of simulating thermal load cases, but yeah, you can do from soak temperature, but then you can also go further and apply different temperature loads for different lenses. You can connect it with a whole FEA analysis. So if you do thermal transit thermal loads in a FEA solver, you can then bring that over into Zemax and look at the optical performance.
Thank you.
No problem.
Thank you for the question. Great. Oh, is there any other question here? Okay, then we can move forward. Anyways, if you have any question, also you feel free to ask, or at the end of the presentation we have also a Q&A session. So great. Let's move forward. So what I wanted to explain you here is just a story about how a customer was successful with using our optics simulation tools. This is the story of the James Webb Telescope. Just to give you some context, so for decades, the NASA Hubble Space Telescope has provided images of distant galaxies and stars. And since 2021, the NASA has launched a new telescope called James Webb Telescope, which can collect now 6 times more light than the Hubble and longer image wavelengths. So it's a much better option. And to be able to design the optics of the satellites, it was challenging for them because they needed to create a structure that can operate in permanent solar radiation. And its structure had to fit had a size of a tennis court that had to fit into a rocket. And it needed to fly over millions of kilometers in the space and provide high resolution images from the deep space. So they choose to use optics simulation for virtual prototyping, and they were using Ansys CMAX Optics Studio for simulating the complex optics of the individual gold-plated mirror segments in the telescopes. So you can see here some examples about how they were doing some ray tracing through these mirrors. And here how they were doing some mirror alignment after checking how the radiation were affecting into the mirrors. So using simulation, they were able to design, optimize, and validate these mirrors, considering how the irradiation will affect the optical system in the space. So they didn't need to do physical prototyping thanks to CMAX, and this has helped them to save significant cost, predict potential errors, validating the optical components, and also to mitigate potential risks. So let's move now to deep dive a bit more in what you can do with each of the solutions that we have at Ansys Optics. So let's start with the nano components. Let's start with Ansys Lumerical. So with Ansys Lumerical, as said, is that we are going to use for the photonic simulations of sensors, waveguides, micro lenses, and all of these components at a chip level where optics are required. And you can do things like the ones that you can see here. So nanostructures, waveguide electro optics, light sources, things like detectors, meta lenses, and gratings. Things like solar cell design, anti-reflective and highly reflective coating analysis, and also for photonic integrated circuits, so for PICs design and optimization, which is a very important use case for telecommunications, for example. So let's have a look again at the challenges that you can have when you need to design optical components for free space. So one of the main challenges is that you need to be able to reach the satellite requirements. And sometimes optical systems, the optical systems that you had in mind, are either too big, they require precision for assembly in the satellite, or they can be simply very expensive. So optics for free space optic systems need to be compact. They need to require less energy. They need to be very reliable to establish a very good communication. And the solution to that challenge is really to use or design integrated photonics, because integrated photonics are small, lightweight. They don't require moving parts. They don't need to add any. You don't need to add any mechanics on it, and definitely Ansys Lumerical is the tool that you can use for simulating and optimizing and design from scratch these integrated photonics that can help you here. So at Ansys Lumerical, we have a comprehensive set of tools, what we call with multiple solvers, that can help you in different use cases depending on what you need to do. I'm gonna guide you quickly about what are these solvers to give you a high-level overview about what you can do with each of the solvers. So we have first Lumerical FDTD. This is a this is a solver for Monte Carlo equations in 3D. So you can with it design any kind of photonic components in 3D for any application, basically. You have also Lumerical Mode, which is a 2D solver, which is mainly used for waveguide simulations. It can be, as it's in 2D, this is a very fast simulation solver. You can also have Lumerical Multiphysics, which is the tool that you're going to use for photonic simulations that require to add electrical components, quantum, thermal effects to understand how these multiphysics are gonna are needed in these photonic components, or can change the designs of your photonic components. Also to mention that we have numerical accelerators. This is to scale up the simulation speed, because Lumerical can work with GPU and high-performance computers, so up to you how you want to speed up the process with the Lumerical accelerators. We definitely have many options here to scale up. Another important one is Lumerical Interconnect, which is the tool that you're going to use mainly for photonic integrated circuits. So this is when you have designed the different photonic components with all of these solvers, you need a tool like Lumerical Interconnect that can help you to simulate in a schematic way. So do a schematic visualization to understand how the photonic components will fit into a circuit. And it also has with a big library of that you can use from some predefined components that you can add into your circuit. And finally, we have CML compiler. CML compiler, this is the tool that we are going to use which comes with a big library of other components predefined that you can add into your circuit, also for photonic integrated circuits. Also to mention that Ansys Numerical works with foundries to develop simulation models for their photonics PDKs. The goal of the goal here to collaborate with these foundries is to enable scalable and reliable integrated photonics for everyone. Okay, so this is an example to show you why. So, for example, photonic designs can be really decisive in the design of an optimization of photonic beam steers. So, just take the sample of beam steers. There are several techniques used to change the direction of a laser beam, like the following ones, like optical phase array, focal plane array, and dispersive gradient diffraction. And these techniques requires silicon photonics, and Ansys Numerical is the simulation tool that can help you to design and optimize photonic components to apply these techniques. Another example is quantum key distribution. So quantum key distribution is a secure communication method that is used for free space communication. And it's interesting because it's a very secure communication method. And it requires of the design of photonic components like the ones that you can see here. So you can design all of these components using numerical mode, numerical FDTD, and also multiphysics. But once you have designed all of these components, you need to fit all of these components into a circuit. So for that, you will use numerical interconnect. And with that, you are able to conduct some light from a source into a circuit, but you need to be able to capture the light using an optical system. And to be able to design this optical system, you need to jump into the next tool. You need to jump into macro optics, which is what we are going to explain later, which is Ansys CMAX. So again, let's jump into the macro optics design. This is where we are going to use CMAX Optics Studio. CMAX Optics Studio is the tool that we use for modeling of macroscopic optical components. And I'm going to guide you through the different functionalities that you have in a high-level overview on CMAX. So first is you can use CMAX for sequential and non-sequential ray tracing. This is to visualize how the light is going to travel through your optical system. Also for designing the lenses, including multiple materials and add different coatings. You can do some tolerance analysis. So this is to analyze the impact that manufacturing variations will affect your optical system. Once you have done that, you can do the performance optimization. So you can use it for analyzing the designs and performance of your optical system. Also to mention that it offers a full interoperability with other Ansys optics tools like Numerical, like Ansys Peos, and of course tools from the Ansys family like Optics Lang for optimization, Mechanical for adding some mechanical components, STK, and other solutions from Ansys. And finally, you can do multiphysics simulation. So CMAX allows you to analyze how thermal loads will affect your optical components. So what we call stop analysis. And again, this is going to be a part explained a bit deeper in details by my colleague Florin Herren. Okay, so
may I ask a question?
Of course.
You mentioned earlier, sorry, I'm losing my voice again, that you would use numerical for meta lens design. So
Yes.
say you want to design a meta lens component, but then place it within the context of, let's call it a a classical optical system, a macro optical system, you would require both numerical and Zmax, but how does that interaction work?
So there is thank you very much for the question. So actually at Cmax we have different solutions. So you have a Pro edition, you have a Premium edition, you have an Enterprise. But basically, just to answer your question, there is an interactive way to export files from Lumerical into Cmax through a dynamic link. Yeah, so it allows you a much better interoperability since we have this interconnectivity now.
And how would the optimization then work? Would you have both Lumerical and Zmax running concurrently? And if you do optimization in Zmax, Lumerical would be responsible for the optimization of that meta lens.
I think that you will create a bidirectional workflow. I don't know, Florin, who is more the technical expert on this side.
Yeah,
You can
I can jump
give a bit
jump
better.
in here.
Yeah.
Yeah, you would go, so the file format between Lumerical and Zmax, where you can design the metal and surface in Lumerical, then bring it over into Zmax to do traditional lens design analyses. The file format is called a JSON file. And you would go through, if you want to do your full optimization, you would go through a loop basically of both solvers. However, there are some first pass optimization capabilities within Zmax directly already, which can alternate some parameters of the JSON file. We do have an article. I'm just trying to find it while Alvaro was speaking. I can send that in the chat. The article should be open access, so you can just read it through on the workflow, how to bring it over meta lens surfaces from one to the other.
Thank you. That would be interesting.
No problem.
Thanks.
Thank you for the question. Okay, so any other questions so far? We can move forward. Okay, so let's move forward.
Just something else is you touched on in the numerical world coatings, IR coatings and different coatings. Is that does the solver cater for that as well? So if you have a macro lens and you apply coating to one surface with the analysis, would you be able to look at the effects of the coating on the macro system if you apply the coating in numerical? I think that's the question.
So if you apply the coating into numerical, what you have done in Cmax, you mean? Or there's no Cmax here?
Can you, yeah. So the effect of coating, say you want illumination over field, and the coating might affect that. Can you apply the coating and analyze that? So do you cater for applying coatings and looking at coatings?
I can maybe take that.
Coatings, yeah.
So in Zmax, yes, we are applying coating. You can apply coating on the lenses, on the mirrors. You can optimize towards specific coatings. What we're doing, we have several ways of defining coatings. In Lumerical itself, you can do, especially with the FDDT solver of Lumerical, you can apply a thin film coating, but because Lumerical is basically designs on such a small level, you can also just completely outright design your coating as its own optical element, because it solves the wave equation completely and doesn't make any ray tracing approximations. Okay. You can also just design it.
Okay, thanks.
No problem.
Okay, so then let's move forward. Thank you also for the question. Let's move to the next slide. So what I wanted to show you here is an example that explains how you can use CMAX for the design and optimization of mirrors of an optical system. So here we have done a ray tracing sequential mode visualization to understand where the rays are reflecting. And I can find that there are some rays that cannot go through. I changed my analysis into non-sequential ray tracing visualization, non-sequential mode, to create a hole where the rays need to go through. So here I have cut the mirror in the way in the part where I want the ray to go through, and in the last image I can see that the rays can now pass through the mirror and they can now reach the sensor. So once you have done this type of ray tracing and you have adapt the components as you want with CMAX, so you can do some system performance analysis. So you can verify your system performance basically, and you can have different type of visualizations like the ones that you can see here, spot diagram to see the accuracy of your optical system, image viewer to simulate to see the type of images you will get with your optical system, detector viewer, and so on. So now we were, let's say, if we follow the story, so we were able to do the photonic design and optimization. We were able to analyze and, well, design, optimize your macro optic to validate if the optical systems that generated are working as expected. And this is where we jump into the next Ansys SPIOS. So SPIOS is the tool that we will use for system level modeling in full 3D environments. And as I said, you can generate a 3D image of the optical system, and also to have a 3D scene of the final results that I'm gonna get. And just to mention a couple of functionalities that you can have on SPIOS. So first, it's integrated in SpaceClaim, which is a CAD tool that comes with SPIOS that allows you to add some CAD components into your designs. If you are working with any other CAD provider, with any other CAD solution, no problem. You can import any CAD files into SPIOS, and SPIOS works very well with any of those. So it allows me to add all of these mechanical components into my optical analysis, which is going to be crucial when we do, for example, things like stride analysis. You can do then things like aero-optical effects. This is a simulation to understand the behavior of the cameras that can be placed in the air and exposed to vibrations, for example, created by turbulences. This kind of simulations you can do as well. It allows you with it comes with GPU performance to speed up the simulation time. This is crucial when you have to do heavy simulations and you want to speed up the process. So it really helps customers to optimize their simulation time from days to hours. It's really a very important functionality. And as I mentioned before, stride analysis. So you can design. So with SPIOS, you can design mechanical components or import these CAD components, and then you can add these components into your optical system to do very accurate stride analysis. I will explain that in the next slide. Optical design means that it's a tool with a big library of predefined optical components that can be added into your system as well. In system validation, as said, you can analyze how your system will behave in different environment and atmospheric conditions, things like rain, fog, different sun angles. And for example, you can also analyze how the irradiance will affect your optical system. So I said previously that you can do very accurate stride analysis using CMAX and SPIOS, and I will explain why. So when do I need stride analysis? This is simply needed if you want to understand if your optical system will generate unexpected results in your images, things like lens flare, scattering, light leakage, things that I don't want to have in my final result. And the workflow that we will propose you, it's touching two solutions. So in the step one, we will recommend you to use CMAX Optic Studio for doing some ray tracing visualization to understand how the light is going through your optical system. In the next step, you can do some analysis to analyze which reflections are creating the optical components. So what we're going to do some ghost analysis to understand if there are some reflections already generated by the optical components without the mounting components. And then, as I said, that SPEOS is very powerful when you have to add any mechanical components. We recommend you to export the analysis that you have done with CMAX into SPEOS. For that, we have a specific file format ODX that allows you to export all what you have done on CMAX into SPEOS. And as I said, you can also add any mounting components from any CAD system that you have to generate this type of image in which you can analyze in the combination of your optical components with the mounting components. And here it gives you the possibility to analyze if there is some scattering effect generated by the mounting components when the rays are hitting the mechanics. So then the next step will be to use SPEOS to generate a 3D image of the final scene that your optical system can provide. And if the results are not as expected, you can start again adapting components using CMAX. So this will be the perfect workflow if you want to have accurate stride-light analysis, taking in consideration not only the optics but also the mechanics on your optical system. And the next part is going to be the multiphysics workflow for a low Earth orbit satellite done by Florin. So Florin, should I
Great.
stop sharing?
Yeah, you can. I
Okay.
can take over. Perfect. All right then. Okay, now I need to find where we were. That was here. Perfect. Maybe before I get started, I did put some articles in the chat. I hope you've seen those. If not, let me know. You can also reach me via email and ask where to find these articles. I'm happy to send those links over. Great. All right. So Alvaro gave a really nice and detailed kind of overview of the optical portfolio of Ansys. And now I'm going to present more of a specific workflow using mainly ZMAX as the Ansys optics solver, but even goes beyond Ansys optics. I think Lara at the beginning has showed that really nice slide of all the Ansys products. Obviously, we have way more than just numerical SPEOS and ZMAX. We have structural solvers, fluid solvers, mission level solvers, and this workflow of the low Earth orbit satellite is quite a nice example of using all these solvers together in one coherent workflow. And it all bases on the concept of the stop analyses. So what is the stop analysis? So stop analysis stands for structural, thermal, optical performance, and it allows engineers to consider the impact of thermal loads on the optical performance itself. So what we have is we have a nominal performance of our optics in our solver, and then we want to assign structural or thermal load cases on our optical performance or on our optical system to see the optical performance of the degraded system, and that's exactly what we want to do. So stop analysis is used by nearly all our users. So it's used in all industries basically. it can be used in laser manufacturing. There, for example, you would have the thermal load case of the laser itself. So the laser itself is heating up the lenses, which will cause an effect on the optical performance of the laser. Cell phone camera lenses, there are very, very specific aspherical structures, which are very sensitive to structural and thermal load cases. So really good to be able to simulate those cases in that area as well. Aero optics, obviously, we can bring in fluid dynamics here, which is also really important to see. And also, last but not least, in space optics, the environmental condition in space obviously affect your optics, and that's something we want to simulate because simulation is always cheaper than prototyping. So let's look at the workflow itself. And Alvaro has already teased it a tiny bit. So we are looking at a 3U low Earth orbit CubeSat. So a Cube satellite. These Cube satellites are obviously very good because they're standardized in size. So you can just buy off on the launch. You can buy off a bit of space, and you don't have to be leading the whole launch. And these are kind of these 3U CubeSats. So we have a 3 times 3 cubes of 10 centimeters. You can see here the first 2 cubes are used for the optics, and the third cube is used for the electronics. And this kind of CubeSat design itself was taken from a paper of the optical design of the Journal of the Optical Society of Korea. And we just took it because it was a nice example, so we just used it as our template to go through the whole workflow. So how does the workflow actually work? So we are starting off with our nominal design in Zemax of the optical components. What we can see here, there are only 2 mirrors here. So we have a primary and a secondary mirror. And then we are designing the optomechanics and the housing around our optics, and that's done in a CAD environment. And then we have the whole optomechanical geometry. And with that optomechanical geometry, we then doing some mission level analyses. So we are looking at a trajectory in orbit where our CubeSat would be operating. And based on that orbit, we can calculate some incident flux on our payload itself. That can then be converted into a thermal modeling. And based on that thermal modeling, we can run an FEA analysis. So we can then see what happens on our mirrors itself. From that FEA analysis, we can generate FEA datasets, which we can feed back into Zemax itself to assign these FEA load cases on our optical components inside Zemax, and then we run a new ray trace, and then we can look at the performance dropping based on these real world conditions. So let's go through it kind of step by step. So let's start off with the nominal optical and optomechanical design. So here you can see the optical design done in Zemax. We can see here a primary and the secondary mirror, both rectangular, and our design specifications are really, we are optimizing our 2 mirrors to have diffraction limited spot sizes at all fields and a certain contrast. So the MTF needs to be a certain value. Here is 25% over 80 cycles per millimeter. And that looks a bit like that in the analysis tools of Zemax. So you can see here we have the spot diagrams on our system. I actually have Zemax open in the background as well, so I can quickly show that as well. This is how the nominal optical system would look like in Zemax. So we have here, as I said, the primary and the secondary mirror. Light comes from here into our primary mirror, gets reflected onto the secondary, and then is collected onto this image plane, which would be the CCD or the CMOS sensor of our image. And you can see here we have our spot sizes based on our fields which we have defined, and here we have the MTF given at given of our which gives us an indication how well our camera is actually performing. So let me go back to my slides. So here we have these analyses or these results after optimization, and these are done in a room temperature. So what we can do now is we can now take this. We have designed the mechanics around it in our CAD environment. So we have exported the geometry of our optical system as a step file, and then we have designed the mechanics around it in a CAD environment. I've used Creo here, but obviously loads of CAD solvers are available. Then what we're going to do is we use Ansys SDK. And SDK is a mission level solver. So SDK has loads of capabilities. We can analyze and visualize complex system within the context of a mission, but the most important thing, we can create orbits for a satellite. And based on these orbits, we can then determine kind of the environmental effects, so the solar flux, for example, on our payload or on our satellite. So we are creating the orbit. For this mission here, this specific orbital data was decided on. Obviously, we are in Leo here, and we are facing. So we have these kind of these measurements with the semi-major of 7,000 K. And based on these orbital elements, we then get a solar flux of these with these values, and we are then able to bring that orbital. So we are then slicing up our orbit into 24 evenly spaced points. So we're taking the orbital flux at 24 different points along the orbit, and we break it down into these specific points to evaluate the incident flux. And what we then can do is we can bring that flux data or that solar incident flux into thermal desktop, and thermal desktop would be the next solver in this workflow. So Ansys thermal desktop is really for thermal modeling of a system. So what we need to bring into thermal desktop is really the orbit data from SDK, but also the optomechanical geometry, because now in thermal desktop it's the first time we're actually looking at the geometry itself, because it's important to have the specific given geometry, because obviously when we're applying all of this onto a satellite, it depends how the satellite looks like. So our inputs are, as I said, the optomechanical design, and the energy sources, which we get through the orbital analyses in SDK, and then we also need to define the material and the optical properties of our optomechanical design. We are then doing a setup on the finite difference and the finite element object. So we are mapping basically the heat load onto our satellite here, and then we are applying these thermal results on the primary and the secondary mirror. So you can see the time step, and this was the time of our whole orbit, but we are obviously only taking the worst cases here. So the primary worst case with the max temp and the min temps of our mirror. What we then need to do, we need to thermal map from the thermal desktop to Ansys Mechanical. And Ansys Mechanical is the FEA solver in this workflow. So we need to take these nodes from the thermal desktop analyses and convert them into FEA meshing. So you can see here this is the primary mirror. This is the backside of the primary mirror with the retaining mechanics, and you can see then here we are meshing this way finer, and we are meshing this in an FEA way to do structural analyses based on the heat loads, which we just simulated in Thermal Desktop. Once we have that heat loads from Thermal Desktop moved over to Ansys Mechanical, we can do some structural analyses there. So we are slicing this up into very specific meshing. So obviously the front surfaces of the mirror where the rays are reflected or the light is reflected, that's where we need to have the finest mesh. Everything else can have different meshes. So we're just optimizing the mesh where we are interested in. It's usually more accurate mesh. We're simplifying the optomechanics a tiny bit and define cross-section. We're defining connections between the mechanics or the mechanics and the optics. And then we also really making sure that the input and output of the thermal desktop analyses and FEA is at the right side. So we're making sure that these knots, the input and output knots, are evenly matched. And so then we group these mesh and contacts and also the input and output control of the thermal desktop analyses and of Ansys Mechanical. Then what we can do is we can import these loads, and then we can visualize these load cases here in Celsius, visualize these in Ansys Mechanical, and based on these thermal load cases, we then know the deformation or can simulate the deformation on the mirrors itself. So based on the heat load on the whole system, we can simulate a structural analysis on our system. And we just take out the front surfaces of both mirrors, because for an optical sense, that's all we care about. So you can see here, we're then exporting the front surface of the primary mirror and the front surface of the secondary mirror with a plugin inside Ansys Mechanical, and this is called export to star, star being the multiphysics model of Zemax. And we are exporting these as FEA data sets, and which we can then bring into Zemax for optical simulation. So we are exporting those in Ansys Mechanical with select the surface, the coordinate system, and everything. So then we have them in the right format with this little plugin here. And what we then have, we have ready-made FEA data sets, which we can feed into Zemax again, where we initially designed the nominal optical system. So with the multiphysics tool of Zemax, which is called STAR, we are loading these FEA data sets, and you can see here in Zemax, we are then assigning those and fit them numerically onto our optical system. And then what we get is we have a fit assessment as well, so we can make sure that the data is fitted properly over our system. Here, this is the primary mirror. And then we can immediately see the performance of our system is dropping. Because obviously, due to the thermal impact, we will have deformation on our mirrors. And even if they're only really small, they will have an impact on our optical performance. So we can use the performance analyses to see which of the mirrors is contributing more to a spot size increase. We can also use all of the analyses range of Zemax. So all of the normal analysis tools which you would have in Zemax, which you have been using as well to design and optimize the nominal system, will now take into consideration these FEA data sets. So you can see here, before applying the FEA data on the left-hand side, where we have these spot sizes for our nominal performance. And as soon as we apply the FEA data, we can now see that our average spot size is growing a lot more. So here's 15 times bigger, more than 15 times bigger. And you can see here, this is the airy disk, so the diffraction limited section of our light. and here you can see it's in the middle. So it's not diffraction limited anymore at all. So we're out of spec. Same with the MTF. You can see the MTF is dropping massively with after we are applying the FEA data. And yeah, this was kind of the summary. This was kind of the workflow which I wanted to show. You can see here we used the whole chain of Ansys solvers to design optics, to then do mission level analyses, to bring the information from the mission level analyses into thermal modeling capabilities, and then do an FEA analysis. And the results of the FEA analyses can then be fed back into the optical system design and optical system analyses to really get a feeling of how would our CubeSat here perform under real life conditions. And I think that is back to you, Alvaro, or maybe we can take some questions now or later.
Thanks a lot, Lauren. I think there's a question from Andrew. So yes, you can go ahead, Andrew.
Hi, Florian.
Hey.
Look, let's say you want to maybe integrate some thermal radiation shielding on your CubeSat. Are you able to also simulate its effectiveness on the system level? Oh, okay.
Yeah, so if you would have some sort of a shielding, you'd obviously need to design that, presumably in CAD, and then you bring that into thermal desktop, and there you can see the effectiveness of that, because you could have an iteration of your CubeSat with and without that thermal shielding, and then you can definitely see the difference on the optical performance.
Okay, thank you.
No problem.
Any other questions before we go ahead? I think nothing at this stage, Alvaro. I'll hand over to you there now to go ahead. Thanks a lot.
Let me share my screen again to finish my part. Can you see my screen again?
Almost.
1 second. Yes, now we can.
Yes.
Yes, perfect. So
perfect.
Before we jump into the where you can find some additional information, I wanted to give a summary of the key benefits of Ansys Optics. The next slide, if it moves. Yeah. So first of all, you will be able to do precise simulations of complex optical systems using our tools, as you have seen with the 3 solutions that we have. And also in a workflow, like for example, the one that you have seen with Flurin, we will be able to improve the reliability of your optical systems, because Ansys Optics includes thermal and structural analysis to understand how these effects will affect to your system, as we have seen in the previous example. You will be able to definitely reduce prototyping costs using digital prototyping. This is clear. Ansys Optics will help to design systems that are meeting the expected standards. So if you have a concrete standards like the ones that we have seen the example of the CubeSat, and you need to feed on these expected standards. So with Ansys Optics, you are going to be able to model everything to make sure that you fit with these standards. And you will be able to so it will help you definitely in the last part. Oh, I forgot innovation and design flexibility. So you will drive innovation, of course, using all of these solutions, and you will have a collaborative engineering solutions, because it's, as you have seen, you can interoperate with all of these different solutions, and with that you will have much better collaboration between different teams, and also faster processes and optimized processes. Okay, So I wanted to show you where you can find some more information in case you are interested in to learn more. So if you are an Ansys customer, you might have access to the Ansys Innovation Space, where you can find a lot of free courses about Ansys products, this part. And then you have also, this is online, open to everyone, the application gallery. So if you search on Google for Ansys optics application gallery, you will get access to that. And here you have a lot of applications, a lot of different use cases using and combining the multiple tools of Ansys optics. This is a great source also to get more info. And then another source is to learn more. It's to use the Ansys Learning Hub. This is the Ansys Learning Hub gives you access to all product trainings that we have at Ansys, and of course we have a lot about Ansys optics. And yeah, last but not least, follow us on LinkedIn. So we have a page on LinkedIn called Ansys Optics. So it's like a channel. And here we are posting information like customer stories, new releases, upcoming webinars, events where we are going to be present. So yeah, that's also a good source. Feel free to follow us on LinkedIn as well if you are interested to learn more. And this is it from my side. Let's jump into the Q&A session in case you have questions.
I think firstly, just want to say Alvaro and Florin, thanks a lot for this very good overview, as well as the deep dive technical session. So really appreciate it and all the work that has gone into that. Then to the people attending, there's a question from Yazid. So Yazid, you're welcome to go ahead.
Thanks, Laura. Thanks, Alvaro. The question is simply that looking at visualization for the image to show what an optical system would see, is there a way of characterizing a bought-out lens so that we can also do a visualization of that? So, for example, if we wanted to compare a bought-out lens performance to a custom designed one.
Maybe that's sorry, as I'm not a technical expert, maybe Florin, who is our technical expert, might have the answer. Do you know that?
Yes.
Florin?
Yeah. So if I understood correctly, you want to compare a designed lens, a customized lens from an off-the-shelf lens, for example.
That is correct.
Okay. So there are a few ways you can do that. So in ZMax, you can obviously design your optical system, your lenses, just from scratch. So just a customized lens, basically. But we also tap into, we also have a massive library of off-the-shelf lenses, which you can drop into your optical system, which is connected to all the big vendors. So you can go through all the Tor Labs lenses, which you can buy. And then, so basically you can just bring those in as a native ZMax lens and have them in your optical system. What you then can do is you could, for example, you spoke about visualization. So what you could use for that is we have a tool called image simulation, where you can where you can upload a picture, for example. It gets converted to a bitmap, and then you have a visual check because the aberration of your lens will be transported to that image, and so you kind of see maybe a blurriness or a distortion of your system. And you could have the off-the-shelf lens from Thor Labs, or you can have your custom lens which you designed yourself, and you can just do a comparison like that.
This is on the picture itself, because I'm thinking in terms of a lens, not a single lens element. I'm thinking of a lens assembly. So if we were to buy Okay, let's just look at a simple one. A machine vision lens from one of the guys, say Navitar or Fujinon, one of these suppliers. And we now
Yes.
designing our
So
own one, and we want to actually see whether ours is going to be better. Is there a way to do that?
yeah, so you can just use all the analysis tools in Zemax. You can bring in that lens from the vendor. If it's a lens assembly, that's also possible. If it's an intellectual property, they might give you something called a black box. So you're not fully seeing the detailed specs of that lens, but you can still use it in Zemax for a ray trace. So you can just look at the performance and compare the performance of the off-the-shelf assembly or off-the-shelf lens from your vendor or the ones you designed, and you can just compare the results of them too.
You know, perfect. Okay, that was okay. So the black box, we would need the black box performance. To
It
do the
depends, yeah.
calculation.
So if the vendor is really nice to you, they give you the full detailed design, which is usually not the case, because they obviously want to protect their intellectual property, but they can give you a black box, which is exactly done for is a feature in Zemax which is exactly for that. So people can share optical designs and optical systems without giving away the full design.
Okay, thank you.
I can send. I'll also pop an article about black boxes into the chat.
Thank you.
Thanks a lot for the question, and thanks, Florin, and for sharing that article as well. Any other questions? Yes, Piet, you are welcome to go ahead.
This question is about the stray light analysis, joining the optics with the mechanical packaging. So I think you said that is usually done in SPIOS, correct? So it's the combination of optics and the packaging.
Correct.
Yes.
This
right,
part is
so-
done in space, yes.
Okay, so here's my question. The quality of the output, of the accuracy of the output, will depend on how well you have, or the software has modeled the properties of the housing, in the sense of BDRF function, saying or characterizing that material as being, say, native aluminium with a certain roughness, or being coated, being painted, treated. You need to say when the light impinge on that material, what will happen to it. How do you handle it? Do you have libraries in SPIOS? How do you say what is the properties of the packaging material, optics-wise?
Yeah, so I can maybe take that one, Alvaro.
Yes,
So exactly as you said, so in both Zemax and in SPIOS, we can apply BSDF functions to any surface. So you can just apply these scattering function to any surface. So if you design your optics in Zemax, transfer them over to SPIOS with the native file exchange. Then what you do in SPIOS, you start to add your mechanics, which you probably have designed in a CAD. And what you then can do in SPIOS, the material of these optics, let's say they're aluminium black anodized, which is kind of a classic. And then what you would do is you can apply BSDF scattering functions on the surfaces of these mechanical housing. It's pretty straightforward. So we have libraries, and you can even convert the BSDF definition from the Zemax surface function to the SPIOS one. So they're not exactly the same in definition, but we do have a converter as well. So if you set up a BSDF function in Zemax, you can convert it to a SPIOS one as well. I just found the article for that. Here is the definition of the BSDF definition in SPIOS.
Okay, great. Thank you.
No worries.
Okay, so Florian, again, thanks for that and for sharing the article and for the good questions. Is there anything else anybody would like to ask now before we have a coffee break? I think it's all questions has been answered. So thanks again, Alvaro and Florian. It's really good. We will be sharing the presentation afterwards, and they are available for questions if need be during the next week or such. So thanks a lot. So we'll take a coffee break. We've got 5 minutes extra, but we will still start. You can stay online, but we'll start around 11 again with a presentation from the customer case study, which is NewSpace, who will be presenting on how they have been using Zemax. And they're also going to explain a bit how they've interacted and integrated it with the mechanical parts of the products as well. So thanks again. And for those who want to take a coffee break or catch up on work, you're welcome to do that. And we'll start at 11 again. Thank you.
Thank you all for the great questions.
Thanks,
Thank you
everyone.
so
See you
much.
later. Enjoy.
Have a good one. Bye-bye.